Hey everyone, my name is Ajay, and in this section we are going to discuss about the SD-WAN VPN setup. Since we all know we use different type of transport mediums to connect these SD-WAN equipments, so there's also a need of NAT. So we are going to discuss how SD-WAN equipments works with NAT discovery. Before we discuss our VPN, let's talk about some of the basics. So let's discuss what is called the VLAN segmentation. So in the VLAN segmentation, you can see I have a switch 1, switch 2. They are connected with this trunk connectivity, and I have a VLAN 10, 20, and 30. So on these switches, I need to create these VLANs, and these VLANs are going to be the broadcast boundary. So only VLAN 10 can talk to the host reside in VLAN 10. Similarly, VLAN 20 can only talk to the host. Those are the part of the VLAN 20 and 30 as well. There's always a need of isolation, and that there can be various reasons. So we already discussed about how we can create some sort of the boundary when we talk about switches. So it is going to be creating the multiple VLANs, which gives you the boundary between users. Let's talk about WAN segmentation. In the WAN segmentation, we can use VRF, which is virtual router forwarding. And let's take an example of MPLS or BPLS. So MPLS and BPLS basically are the services provided by your WAN service provider. So here is my P router, which is basically the provider edge. This is my P router, which is provider. This is again my P router, and this is again my P router. This is a requirement of connecting multiple customers on one router, which is P router. How do we isolate it? So basically we need to create the VRFs, and all these interfaces, they are going to be the part of those VRFs. So your WAN infrastructure, it is going to be kind of the shared, but we also maintain isolation while creating a multiple routing table. After setup, only customer A can talk to customer A on other side. Similarly, customer B, one side can talk to other customer B sides. There's not going to be sort of intercommunication unless you specify by doing some sort of the route leaking. We can also achieve the isolation while doing the device segmentation. So for example, if you are running Nexus series of the router and switches, you can go for VDC concept. So in a VDC, you can virtualize your chassis in different context. So one context, you might be hosting one of the customers, second context, you might be hosting second customer, and third context, you might be running some different services. And these services cannot talk to each other unless you provision a mechanism of route leaking. Let's come back to our original topic of the discussion, SD-WAN VPN segmentation. So in a SD-WAN, you can see if this is my V-Edge device, it gives me a flexibility to create service VPN, which is the LAN side. Then you have a transport that is associated to the VPN 0, and you can have out-of-band connectivity, and it is going to give you the management VPN 512. So VPNs, they are isolated from each other. Each VPN has its own forwarding table, like VRFs we discussed when we were talking about the WAN virtualization or isolation. VH router allocates a label to each of its services and advertises it as route attribute to OMP updates. We will talk about the OMP and all these things going forward, but let's clear the concept first. If this is my interface, this is another interface which is LAN facing. I can tell this interface is a part of the VPN 10, and this interface is part of VPN 20. So the VPN numbers is a 4-byte integer with a value of 0 to 65535. There's some reserved VPN also, like VPN 0. So by default, when you provision any other device, VPN 0 and VPN 512, it comes by default. Then you have option to choose from VPN 1, and if you leave couple of service VPN, those are reserved. You have a full-fledged range to create line-side service VPN. These service VPNs, basically 10 and 20, they cannot talk to each other. So they are going to maintain the isolation. This side of transport, you can assume this is a shared infrastructure. Whenever the packet goes out, it will be tagged with these kind of the VPN numbers. And on the remote side, based on the VPN number, it is going to maintain its own routing table. We already discussed SD-WAN equipments, they are going to provide you the isolation. So let's try to understand how this end-to-end segmentation works. Here on the diagram, on this side, I have a VPN 10, VPN 20. Other side also, I have VPN 10 and 20. When there is an IPsec tunnel which is formed, it is going to carry a label, which is your basically the VPN label. That's how you isolate the routes from each VPN. What is the need of having this end-to-end segmentation? So you might be dealing with some payment card industry and you need to be the PCI compliance. If you deal with healthcare, you might be following HIPAA compliance. You can do the security zoning. So these zones, they don't talk to each other. You might be running the guest Wi-Fi. So you dedicate one of the VPN 10 might be for your guest Wi-Fi and your LAN traffic. That is part of the VPN 20. Multi-tenancy. If you are kind of the hosting organization, you might be hosting multiple customers and you need to maintain the isolation. So create multiple VPNs to achieve the multi-tenancy. Cost reduction. Obviously, it is since you're going to use kind of the shared infrastructure, it is very cost effective. Agility. Since you have a flexibility to add more and more VPNs to create multi-topology, so it gives you the agility. And obviously, while doing all these things, end of the day, you achieve end-to-end segmentation. While we do end-to-end segmentation, each VPN can have its own topology. So for example, if you're running some sort of the voice services and each branch offices, they have VoIP phone installed. So it has to be a full mesh. So all these sites can talk to each other. If you're running hub and spoke, you might be hosting a cloud-based SD-WAN, or maybe it is a data center hosted where all the spokes, they want to talk to those services. There can be need of the partial mesh, and if you want to provision only one site should talk to other sites, you can go for point to point. So it is up to you how do you want to maintain your own topology, but underlay infrastructure is shared, and top of that you can build any topology based on the VPNs you provision. Let's talk about the IPsec framework while dealing with the Cisco SD-WAN. So this SD-WAN is going to use your IPsec. So for example, this is my original data. Top of that, it is going to impose a VPN label. It is going to be ESP encrypted. And then you are going to use UDP. That is something special here. We will talk more about that. And then this is going to be your outer header of IP. So you can call this IPsec UDP mode, and that is something known as ICLES. VS to VS data plane, it uses UDP port 12346 to 13156. Let's talk about some of the benefit of using IPsec UDP mode. So originally, if you go for the IPsec ESP framework, it uses port 500 both sides when you initiate your IKE phase 1, and this port can easily be blocked. If you are using some sort of the NAT devices in between, it is going to use the NAT-T, so that is going to consume port 4500. That can also be blocked. If you have two devices behind a firewall, it is very, or it is impossible, I would say. They cannot distinguish multiple IPsec devices behind upstream NAT. So while having a wide range of UDP ports, the benefit is they cannot be blocked by your ISP. Then you have a NAT discovery, and the NAT-T helps solving the problem while having the multiple IPsec VPN devices behind the NAT. We will talk more about these, what topologies are supported, what is not supported going forward. Let's talk about how the NAT detection works with Cisco SD-WAN. So there's a utility which is session traversal utility for the NAT. You can read more detail in RFC 5389. So technically all the vEdge, they comes with this utility and they act as a client, and vBond, it is going to act as a instance server. So this device might be behind the firewall. So you have a private IP here and the public IP on the firewall. The first request which goes out is a SDWAN request. And when you get the response back from the vBond, it is going to tell this vEdge device, this is your public IP and the port which this server can see or it finds while doing the discovery. So in a response, this public IP and the port is returned back to your vEdge device. Then this vEdge device is going to send a OMP update with TLOC route while telling this public IP and the port is mine. When the vSmart device receives it, it further distributes this information as an OMP update to all the vEdge devices. That's how this whole mapping or discovery of public IP, those are the NATed one, get distributed to all the edge device. You will hear these NAT terms very frequently when you do the SDWAN deployment. So let's talk about those. The first term is full cone NAT. This type of address translation is also known as 101. A static NAT is a translation in which only the IP addresses are being modified. So this is my source, this is my destination, and this is my NAT device. So this XXXX, it can be the public IP address. When my source wants to talk to destination, my packet format looks like this. This is my source, this is my destination, my IP is A, my destination is B, and my source port is XXX, destination is YYY. When it reaches to, or when it crosses a NAT device, my source IP is going to get replaced with the public IP address. And the return packet, the format will look like very similar. XXXX. This is going to be the destination. This becomes my source, which is host B. And when it crosses a NAT device reverse, this becomes my source, which remains same, and destination IP gets changed to the original one. That's how the whole session completes. When we are doing 101 NAT, a third device, which is host T with the IP of CCC, it can also initiate a connection to public IP address on the same port, and it can, and the request will be delivered to the original host. So there is no restriction as such. The second type of NAT is going to be the restricted cone NAT. All this communication looks very similar. The only restriction I see here, when a third party communicates back to the same port and on the public IP address, this is not going to be delivered. So request should only come from the same IP address. So technically, the request has to be initiated first from inside to outside. Then this host can communicate back to the original one. You cannot directly initiate any of the requests directly to public IP address. Now let's talk about the port restricted cone NAT. Here also this communication looks very similar what we have discussed so far. An initiator has to initiate a connection first. Now look at the difference. Even the host remains same. If the source port gets changed to KKKK, this is not going to get delivered to the original host. I have not discussed about the symmetric NAT, and the reason behind when you do the string discovery, it fails because in a symmetric NAT, every request, every time it is going to hold a different port. So it doesn't work. Let's talk about the possible design combination. If you have no NAT public IP address on the both side, IPsec tunnel can be formed. If you have public IP with the symmetric NAT other side, this tunnel can also be formed. If you have full cone 101 both side, this tunnel can also be formed. One side is full cone, another side is restricted cone. This also works. Full cone with symmetric, this also works. One side is a restricted cone, another side is a restricted cone. It also works. Only condition when you have one side is symmetric, another side is a restricted cone, it is not going to work. When you have both sides with the symmetric, it is also not going to work. That is something you need to keep in mind while you design your SD-WAN infrastructure. Let's talk about the design one. So I have a VH device and this is my firewall. On the other side, I have a public IP address which is directly configured on the VH. Left hand side, I might have this 101 NAT or maybe some sort of the PAT IP address which I'm going to use on the firewall. This design, it works. Let's talk about design 2. I have VH device and this is my firewall. On the other side, I have a firewall and then I have a VH device. This time, this public IP address is 101 NAT. This side also I might have 101 NAT or the PAT IP address, and this also works. Let's talk about the design 3. So let's assume this is my VH1 and this is my VH2 on one side. I have a firewall and I have a single internet connection outside. On the other side, I have a public IP address. It can form two tunnels to two VH device, and the NAT discovery, it is going to assign two different ports for these tunnels. So this design also works. Thank you for watching. I will see you in the next video.